Groovy. This is a quick recap on mathematical induction for divisibility problems. I'll also go through a couple of past external exams. So, when we're dealing with divisibility, we are going to be dealing with problems like this, proving that 7 to the power of n minus 1 is divisible by 6. And this one says that it's for all n that are positive integers. Now if I think about positive integers, that just means that n is going to be greater than or equal to 1. There are a few ways that you might see 7n take 1 is divisible by 6 written. You could see it written like this, with this big line here meaning is divisible by. So this statement here literally says 7n take 1 is divisible by 6. It says the same thing with some different notation. Alternatively, we could also set this up like this, by saying that if it's divisible by 6, it's actually going to be equal to 6 times some kind of other integer. So if it's divisible by 6, it follows that it's a multiple of another number. This is probably the most useful version, and this is the one that we're going to keep on using again and again when we come back to these proofs. So 3 different ways of saying the exact same thing here. Let's actually do the problem now. First step is always going to be the basis step. So I'm going to check that n equals 1 works. So is 7 to the power of 1 take 1 divisible by 6? Let's check. That's going to be 7 take 1 equals 6m, 6 equals 6m. Cool. So this works. I'm not trying to calculate m, but the fact that I've got 6 equals 6 times something means I'm done. And this is the easiest way to set these divisibility problems up. Your end goal is to get 6 equals 6 and then have something else there. I'll show you what I mean by that in a moment. Now I'm going to do my inductive step. So first of all, I've got to assume that n equals k is true. And just like with our addition problems, I'm only going to substitute any n's that I see. So that would mean that 7 to the power of k minus 1 is equal to 6. Now I shouldn't use m again because I've already used m and it could be a different integer. So I'm going to use p. Lovely. Now I'm ready for my proof. So I'm now trying to prove that 7 to the power of k plus 1 minus 1 is equal to 6. Again, I shouldn't use p, I shouldn't use m. I'm just going to use something else. Now just like with our addition, we're still going to want to substitute something from this step here. We don't have a sum to deal with this time. So this is going to hinge on us rearranging. So what I could do is I could actually rearrange this expression and make note that 7k is actually equal to 6p plus 1. I'm going to set this as my first expression. Rearranging like this is a really easy trick that works every single time. When I look at my proof here now, I'm going to look for an opportunity to sub in 7k. So to do that, I'm going to need to do some rearranging. 7 to the power of k plus 1 is exactly the same as 7 to the power of k times 7 to the power of 1. And straight away I can see where I'm going to substitute in. So I'm now going to write that 6p plus 1 all multiplied by 7, take 1 equals 6r. I'll distribute the 7, I get 42p plus 7, take 1 equals 6r, I get 42p plus 6 equals 6r, and my last step here, remember, is to make sure that I have 6 equals 6. So I'm just going to pull my factor out, so I get 7p plus 1 equals 6r. Now I'm done. I've got 6 equals 6. That's all I was looking for. QED. For my statement, which I know the external exam is probably going to want, I would say that 7 to the power of n, take 1, is divisible by 6. Lovely. Now in regards to past EA questions, we've got a few here. You've got 2024 paper 1 question 3, which I'm going to look at first. You've also got question 16, which I'll have a look at too. Then you've got the 2023 alternate sequence, paper 1 question 2, also question 15. Then on the 2021 alternate sequence, you've got paper 1, question 13, and question 18. I'm only going to do walkthroughs for 3 and 16 from the 2024 paper, and then question 18 from the 2021 paper, because it's pretty neat. You'll notice that all of these are paper 1s, because induction doesn't really require calculators. Let's have a look at 2024 paper 1 question 3. So it says, consider a proof of the proposition, blah blah blah, using mathematical induction. Within the proof of the inductive step, the proposition for n equals k plus 1 could be expressed as. Now the trick with this question, and this is a really common EA question as well, this one comes up heaps, almost the exact same kind of structure. The trick with this is really quite simple, but it's easy to get lost in if we aren't careful about exactly what it's asking us to do. Excuse me. Hello. Lovely. So I'm going to start with my expression, and the easiest thing for me to do is I'm going to write what my n equals k plus 1 proposition should look like. So anywhere that I see n, I'm going to substitute in k plus 1. Remember that if it's not an n, I'm not substituting k plus 1. So straight away, I can see that B and D are out, because there's an error here in understanding in that the J's been subbed in when we shouldn't have done that. We should only substitute the n. Now I can simplify my right hand side here. K plus 1 squared is going to give me k squared plus 2k plus 1. So that would show me that the correct answer is A. Done. This is very common. This is a really easy gotcha. The next one I'm going to have a look at is the 2024 paper 1 question 16. And the reason for that is because this is a nice, slightly trickier divisibility problem. Now, when we look at this, you might notice that we've got more than one term that's to the power of n here. 6 marker, it's a big question. There's no scaffolding along the way. So because there's no scaffolding, this is a complex familiar building. Let's get into it. First step always is my basis. So I'm going to check for my base values. Now, if n's a positive integer, it means it's going to be greater than or equal to 1. So is 12 to the power of 1 plus 2 times 5 to the power of 1 take 1 a multiple of 7? Let's have a look. That's going to be 12 plus 2 times 5 to the 0. That means 12 plus, now 5 to the 0 is 1. So I get 14 equals 7m. Now again, I don't care about m. I just care about is it divisible by 7. Yes, it is. You could have stopped here, that would have been fine. But I'm just going to this next step just to be consistent. Now I'm ready for my inductive step. So I'm going to assume that n equals k is true. So that means that 12 to the k plus 2 times 5 to the k take 1 is a multiple of 7. Then I'm going to prove n equals k plus 1. So once again, I'm going to substitute my k plus 1 for anywhere that I see an n. And it's still got to be a multiple of 7. So again, I'm going to look to substitute something from my inductive step. This is pretty easy to rearrange. I'm just going to rearrange from my 12k and kick everything else over there. And this gives me something really easy to substitute in. Because if I expand this 12k, I'm dealing with 12 to the k times 12 to the 1. I can simplify this to just 5 to the power of k. I'm going to sub in 1. And so that means that I'm actually dealing with 7n minus 2 times 5 to the k minus 1 dot 12 plus 2 times 5 to the k is equal to 7p. Alright, so I've still got this k in here, but let's just sort of work with it and see how we go. I don't want to sub something else in from back up here because I'm going to end up into a bit of a loop. So now that I've made my substitution, I'm just going to stick with it. So I'm going to distribute this 12 first of all. 12 times 7 is going to be 70 is going to be 84n. Take 24 times 5 to the k minus 1 plus 2 to the 5k equals 7p. Now I want to somehow combine these terms together, so I need to make them look exactly the same. There's a few ways you can think about this. Probably the easiest one is I'm going to express my 5 to the k minus 1 like this. And then that would help my brain go, okay, cool. Well, that's going to be 24 5k. Now 5 to the negative 1 would be on the bottom, right? And then this is wide open now. So I've got a 5 to the power of k here and a 5 to the power of k here. To add these, I'd better make 5 a shared denominator. Now I can add them. Negative 24 plus 10 is going to give me 84n take 14 times 5 to the k on 5 equals 7p. And straight away I can see that I've got my common factor of 7 here. So 7 times 12n minus 2.5 to the k. Now you can leave it as 5 to the k on 5, or if you want to turn it back into a k take 1, you can definitely do that. Either one's fine, completely okay. Equals 7p, and I'm done. So that means that, and I'm going to just stick with this habit of writing the statement because that seems to be what they're really liking. That means that 12 to the n plus 2 times 5 to the n minus 1 is divisible by 7. Some kind of statement to that effect. Now the last problem that I want to look at is a great question. It's this doozy. 2021 alternate sequence, paper 1, question 18. It's a doozy because, as you can probably see straight away, this is a combination of topics. So the moment you see a combination of topics like this, you know that you are dealing with a complex unfamiliar problem. What makes it a combination of topics? I can see that I've got both some trig work in here and some mathematical induction work. So I know that I'm going to have to be dealing with both of these things in some way, shape, or form. Let's dive in. It says that n is a positive integer, so that means I'm dealing with greater than or equal to 1. I'm going to start with my basis step by proving that n equals 1 is true. And let's have a look. So that would mean that the sum, this is a terrible sum, of r equals 1 up to 1 of 2 to the r take 1, 10 of 2 to the r take 1 theta equals cot theta minus 2 to the 1 cot 2 to the 1 theta. Now, because my left-hand side here is the sum starting at the first term and finishing at the first term, I'm just going to use the first term. So that means I'm going to be looking at the first term equals cot of theta minus 2 cot of 2 theta. Alright. 2 to the 1 take 1 is just going to be 2 to the 0, so that'll be 10. 2 to the 0 gives me 1, so tan theta equals cot theta minus 2 cot of 2 theta. Alright, so now I need to prove that these two things are equal. So all of a sudden my induction problems become a trig identity problem. I'm going to use my good old trick of expressing tan and cot as exactly what they are. So sine over cos equals cos over sine. Take 2 cos. Now be careful here because cot of 2 theta is going to be equal to cos of 2 theta on sine of 2 theta. So straight away I can see that I'm going to have to pull a double angle identity out of the bag. You've got a couple of choices here because, well, you've got a choice for your cos double angle, you don't have a choice for your sine double angle. as always, depending on the path that you choose, it'll either be pretty easy and have 1 or 2 steps, or it'll be pretty hard and have quite a few steps. Now, cos of 2 theta, when I look at my formula book, I've got 3 different options here. I'm actually going to go for the very first one, which I wouldn't usually do. For sine of 2 theta, now note that sine of 2 theta is 2 times sine theta cos theta. So that does mean that these two 2's will cancel. Alright, now when I have a look at this here, I can see that I've got a sine theta and a sine theta. If I multiply everything by cos theta, then I'm going to have the same denominator here, and I'll be able to add them together. So that's going to be the first thing that I'm going to do. So that's going to look like cos times cos is going to give me cos squared theta divided by sine theta cos theta. Take away cos squared theta, take sine squared theta all over sine theta cos theta. Now when I look at my right hand side, also my left hand side now, I'm going to multiply that by sine theta on the top and the bottom, just to get all of my denominators exactly the same. Cool. So now I don't really care about my denominators at all. And let's have a look what we got. We've got sine squared theta equals, now cos squared take cos squared is going to cancel, and then negative sine squared is just going to give me positive sine squared. So we get sine squared equals sine squared. Cool, so my base step works. Now I'm ready for my inductive step. So I'm going to assume that n equals k is true. That's going to look like the sum from r equals 1 up to k of 2 to the r take 1 10 I'm actually going to turn to this problem and yeah, 2 to the r take 1 10 times 2 to the r take 1 theta equals cot theta take 2 to the k cot of 2 to the k theta. That's my inductive step done. So it's worth noting, if it helps, that this left hand side is really, we start with 1, we add the next term, and we keep on adding until we get up to the term that is 2 to the k which is all equal to this expression on the right hand side. Cool. Now I'm going to prove that n equals k plus 1 is true, i.e. that the sum from, these sums are getting worse every time, from 1 to k plus 1 of 2 to the r take 1 10 of 2 to the r take 1 theta equals cot theta minus 2 to the k plus 1 cot 2 to the k plus 1 theta. As always, this is going to hinge on substituting our second step in, because if I think about my left hand side here, I'm going to start with my first term, work all the way up to my kth term, and now I'm going to have my k plus 1 term. And all of that is going to equal this right hand side right here. Cool. So now I can see that I'm able to substitute all of this out for this. So I'm going to sub that in. So now I'm actually dealing with cot theta, take 2 to the k cot of 2 to the k theta plus 2 to the k tan of 2 to the k theta equals cot theta minus, now I'm going to split this up already here into a 2 to the k cot of 2 to the k. So I'm going to work just on my left hand side here for a little bit. It looks a bit more complicated. I can see that I've got a bit of a match between these two sides already in the cot, so maybe there's a way that I can make this cot tan expression here equal to this singular cot expression here. We'll see how we go. Alright, so first of all I'm going to look at what is shared between these two things, and I can see that the 2 to the k is shared. So that leaves me with cot of theta, take 2 to the k of cot 2 to the k theta minus tan 2 to the k theta. So I guess I've sort of like pulled and kept the negative with it because I've got the negative over here, but it would work the other way still. Now within this, I'm going to see if there's something I can do. Maybe I'm going to express my cot and my tan as my cos minus my sine over cos all still equals my right hand side. Lovely. Now I'm going to I can combine these two fractions by cross multiplying, so I'm going to do that. So that's going to look like this. I'm going to have a cos squared times 2k theta over sine of 2 to the k theta times cos of 2 to the k theta, take away a sine squared of 2 to the k theta on the same denominator now. All of that still equals my right hand side. Can I combine the two things here now? Yes, I can. Cot theta, take 2 to the k. Now cos squared takes sine squared. Is actually part of one of my double angle identities, and this sine of 2 times cos is another one of my identities as well. So I used a double angle identity previously earlier in this question. Now I'm actually going to use that in the opposite direction. So I know that cos squared take sine squared equals cos of 2a, and I know that, now this first identity is a bit mixedy-moxedy, but I know that sine of 2a on 2 is equal to sine of a cos of a. So this looks like my denominator, and then this top one looks like my numerator. So now I'm ready to rock and roll. Now why is this handy? This is going to put some double angles in, and I note that my right hand side has a bit of a double angle going on. So this is a bit of a hint here. Now definitely you could have worked on the right hand side and gone the other way. You would have just gone, yeah, you would have gotten the right hand side to look like the left hand side. So now I'm going to go, okay, cos of 2 theta, so that's going to be like cos of 2 times theta, and theta is 2k theta. Sine of 2 theta, theta is 2 to the k here. Now that's divided by 2. When we divide by 2, we're really timesing by 2. So I've got cot of theta. So when we divide by half, so I can pull that out the front of cos 2.2k theta on sine 2.2k theta. This is feeling pretty close. Cos on sine I can express as cot and 2.2k would be so I can probably do that here. Actually I can go, oh yeah, I'll leave it like that. Theta, and that equals my right hand side, and my right hand side is cot theta minus 2.2k of 2k dot 2 theta, which is really exactly the same as 2.2k theta. Both sides equal. Done. Now again, you could have worked this right hand side through instead, hinging on this double angle identity, and you would have taken it all the way back. You would have just ended up going backwards, but it still could have worked. Yeehaw. So a really nice example of a tricky induction problem that involves our trig identities. There's a bit of a theme here. We've seen 2 complex unfamiliar problems so far, both involving trig identities.